In three, two, hello, I'm live now. So Mom Debbie is here. I'll start straight away without much ado. So this is a continuation of the one I have shared today. It's about buoyancy and stability. So now we go to the stability bit of submerged and floating bodies. Buoyancy was already presented a while back, and then stability is now the second part. Right, stability of floating bodies. Example, we have, I will send this and then just go through it. I have here two illustrations of body, a body that is in stable position and in unstable position. So there are two things that you're going to look into. You have the center of gravity here of the body, and you have the center of buoyancy, BO, and the meta center, and also the application of the weight to the G. And here, the G is look, located there above the meta center, and the center of buoyancy is still in place, but it has shifted to BO prime because it has tilted. So with the first illustration, and the meta center is below G. Now, on the first illustration, when M is above the center of gravity, it is said to be stable. Why? Because the body seems to tilt this way, but because the weight will have a counter moment of the tilting that is called the right moment, then it will go back to its original position. Let's remove all this again and I will illustrate. So the because of wind pressure, because of say waves created by other vessels, water vessels, then there could be tilting on the body that is floating. However, if the the weight will make a moment to the meta center in the right direction, that is counteracting the body that is being tilted. Look, there is a moment that causes the body to tilt this way, but because of the weight having a moment to its meta center, then this becomes horizontal after a while. Why? Because it counteracts whatever causing the tilting of the body will be. Okay, so let me just, where are the causes? Hang on. The causes, hang on, please. I have the causes here, why bodies are being tilted, or you can just go through it. I'm disturbing the momentum again. A lot of things to say, right? Okay. Anyway, let's go to an example straight away. So when bodies are in neutral position, upright position, then and the weight and the buoyant force are aligned. Okay? Look, the weight is acting at the G of the body. So this is the body with a height h. So if you're going to divide this height h by 2 from the bottom, h divided by 2, that is the location of the G reference is referenced from the bottom of the shape or bottom of the body. So hey, that's too big. Sorry. It's too thick. Right. So this is the bottom and it's referenced here. How about the what's that again? The center of How about the center of buoyancy? For the center of buoyancy, you can get that from the submerged part of the body. Okay, I repeat, if this is the body submerged and this is the height of the body, then the CG is just h over 2. Okay, h over 2. But when it is submerged, for example, this is the height of submersion, then the CG will be half of that. Okay, the buoyancy of the submerged part, the the center of buoyancy of the submerged part will be half of the submerged part. So here, this is your H2. I will call this one as H1. Okay, H1, H1, H1. Then here will be buoyancy BO. Center of buoyancy will be H2 over 2. You got it? Very good. All right, so let's proceed to an example. I already calculated this a while ago. A rectangular wooden block of dimensions 2 by 1 by 0.5. 2 by 1 by 0.5. As you can see here, the longest side will be 2, and then you have the bottom 1 meter and 0.5 for the height. Okay, floats in water with its largest face horizontal. So this is the illustration. The largest face is horizontal. The density of the wood is 600 kilogram per cubic meter, and the density of the water is 1000 kilogram per cubic meter, which is always given fresh water. So we are going to determine the depth of immersion, how high is the body had been submerged, and what would be the metacentric height. Is it stable or is it tilting? Okay, so we go to the stability meantime. Right. So this is the scenario when it's floating. 0.5 is the height and 2 meters is the length. Let me just remove unnecessary lines in here. Now, another thing that I want to explain here is when the body tilts or when the body will be subjected to rotation, it doesn't rotate like on this face. It doesn't rotate on this face. It rotates on the side. Now, we must know that because it has something to do with the moment of inertia. Okay? So the moment, as you can see here, which I illustrated boldly, the moment will be tilting like that. Okay? On the side. Okay? Not before it or not in front of it. It won't tilt in front. It will tilt on the side. Okay, next question or next slide. All right. Well, I thought I have a different question here. Okay, so what would be the solution? We have to equate, first and foremost, we have to equate the force due to gravity or the weight to the force due to buoyancy. These were already tackled earlier on. Okay, so we'll go to the force due to gravity or the weight. How? This is the P, which is the rho, 600. This is the V, the volume submerged. Okay, the volume submerged. At first, you have to. Well, let me just do it again. Okay, so you have the rho, 600. You have the volume of the body, because this is about the weight. And then you have the G, which is 9.81. Okay. If you multiply this together, let's do it. We have 600 times 2 times 1 times 0.5. That is in cubic times 9.81. Oh, sorry for that. 9.81. Then you get 5886 as the force due to gravity, or the weight. Okay. So that's it. And then you equate this one to FB, which is the same as the formula rho VG. However, it will be a different it will be different values because we are pertaining to the water to which the body is submerged. So you have FG equal to FB this time. We know that FG is 5886 now, and then the FB, the rho of the water, which is 1000, obviously here, and then you have the V. The V will be the submerged volume. So here is the rectangle. It's submerged here, and you don't know the height to which it is being submerged. And then the cross section would be 2 here, and then here would be, hang on, like this, yeah, 2 and 1, 2 and 1, and H. Can you see that? Can you see what I'm saying? Okay, the volume will be 2 length times width of 1 times the height. Yeah, let's go back to the illustration. So this one here, consider this. So the submerged will be 2 here, and then that one, this one is 1 meter, and we don't know the height. We don't know this height. All right. So if you're going to look below, this is 2 meters, this is 1 meter, and the height here, which is H. Okay. I will let you imagine in time. I'm just cleaning up. Okay. Sorry for that. There you go. I don't like a messy drawing. All right. So did you understand about the volume? The 2 in length, and then 1 for the width, and the height will be H. We don't know that. Right. You just comment down below if you didn't understand. But once I give you this copy, then maybe you can understand it better. Okay. I hope I'm giving justice to it. So, because 5886 is on this side, and then you have the rho and the G with a H. So look at this one. 1000 times 9.81 is 9810. And the 2 will be a denominator. The H will be the unknown here. You have to divide all these quantities. That will be your divisor of the 5886. Then you will have a value of 0.3 meter. What does it mean? that the volume submerged has a height of zero point 0.3. Okay, and that is the first unknown in this problem. The depth of submersion is zero point 0.3. Okay, right. Number two. By the way, the H here, we do not know how deep was the block being submerged in the water. Okay, so we know the weight of the block, 5866. Equate that to the buoyant force, which is rho of the water, G, which is due to gravity, and the volume submerged. Okay, the length is 2, the width is 1, and the height is h. We do not know. And we can solve h from there. All right, and we did. It's zero point 0.3. Now we go to the metacentric height of the block to know whether it is stable or not. Okay, when we get positive mg, then it means it's stable. When we get negative, then it means it's unstable. Okay, let's move to the next slide. For the metacentric height, I already had illustrated that the height of submersion is 0.3. Okay, I'll just correct the height mean time, though it's already there, but I just want a better illustration so that the horizontal aligns with what I have on the illustration. All right, so we have here 0.3 meter as the height of submersion. We have a formula, okay? The formula is mg is equal to BOM minus BOG. Please take note on this. It's a very important formula when dealing with metacentric height. What is metacentric height? That is the point where tilting can be reckoned or can be referenced. What causes the tilting? Because of wind pressure and all, but it can still go back if the weight will have the same counter moment to the tilting made by the body due to wind pressure or other disturbing forces around it. They must always be aligned. The metacenter, the G, the metacenter, the G, and the center of buoyancy. Okay, those three must be aligned. Once they tilt, then it's not stable. Okay, here is the formula, two formula here. So mg, the metacentric height, is equal to BOM from M to BO minus BOG. So you can get this one, correct? MBO minus BOG, then you can get MG. I hope that's clear. All right. Let's go to the formula. First off, we need BOM. It's another formula. It's I, or that is moment of inertia about its axis, 112 BH cubed. We learned this from statics, divided by the volume submerged. Take note on this. BOM, or this line here from M until the center of buoyancy, is I, or a moment of inertia, over the submerged volume. Now, for the moment of inertia, let's consider the rectangle in this scenario. Okay, hang on. I'm going to circle it on this scenario. Okay, so when the block tilts, as I've said a while ago in this illustration, when the block tilts, then it tilts on it's 1 meter length. It doesn't tilt in the 2 meter side, but it tilts on the 1 meter length or 1 meter width. Okay, so if that's the case, then you will have this illustration here. You'll have this illustration here. Let's go back there. Okay, so you will have this illustration here. When it is 101% tilted, you have the base to be 1 meter and you have the height to be the 20, no, not 20, the 2 meter length. Do you understand? Do you understand? So 112, the base, the height. And the scenario will be like this. It will tilt on the side. It doesn't tilt inward. It tilts sideward. So where it tilts, then that will be your base, 1 meter. And the other end will be, or the other side will be the height. Okay? This moment of inertia, it's about the turning of the body on its axis. Why is it on its axis? Because the axis is the one in vertical, here, the one in vertical, and it's tilting on that axis. It doesn't tilt or it doesn't rotate in other axis. It's on axis. So 112, the base, the height cube. So if 112, the base, the height cube, then our height here is 2 and our base is 1. Why again? Because the rectangle goes like this. Okay, this is the CG that we have been illustrating. This is 1 meter and this is 2 meters in height. Okay, if that's the case, then we substitute everything. You have 1/12, the base, the height cube, you get 0.667 to the fourth, meter to the fourth. Okay, so that is the unit of measurement. Okay, now substituting it now to our BOM line. The I here is 0.667 meter cube, meter to the fourth, and then the volume submerged will be 2 times 1 times 0.3 times 0.3. That will be the height of the block being submerged. Okay, so 2 meters, 1 meter, and 0.3 will give you meter cube. And the numerator is meter to the fourth. The denominator is meter cube. So it gives us a meter unit, right? So meter unit means it's a length unit. If it's a length unit, then we are particular to a distance value. So we got 100, oh, it's not 100, we got 1.1112 meter. That is BOM. Okay, let's move to the next slide. All right, so for BOG, because we said that mg is equal to BOM minus BOG, okay, to get those distances, right? So we know BOM already, yeah? Now we go to BOG. BOG is, I introduce another variable here, D, at the bottom of the rectangular shape. I introduce D at the bottom of the rectangular shape. Let me just put another color here. Here at the bottom, yeah? You can see D there. Okay. So GD minus GD minus, you can already see from the illustration, minus BOD. Okay, GD minus BOD will give you BOG or GBO. Okay, so we are interested of the orange line. I repeat, the purple is the GD, which is this, and then minus the BOD, then you get the BOG. I know that you're very good at this, okay? I trust you. Let me just erase some of the unwanted lines there now. Okay, hang on. Sorry for that. Did I put it? Oh no. Sorry. It's a waste of time. I know. But I just want to put back that line, isn't it? There. All right. So let's solve for BOG. How? The GD is actually 1/2 the height of the wood. It says here, 1/2 the height of the wood. What is the height of the wood on this side? Is 0.5. So 0.5 divided by 2 gives you 0.25, as you can see from the computations. Okay. So we got that 0.25. And the BOD will be 1/2 of the submerged height. The submerged height is 0.3 divided by 2, that will be 0.15. So having all those halves, then you can now compute for BOG. 0.25 here, 0.25, and then 0.15, you'll get 0.1. All right. Are we okay with that? Please do a comment down below. You say, yes, I am. I'm okay with it. All right. Now we are ready to solve for MG, the center of the meta center. So BOM that we have computed a while ago is 1.1112. The BOG is negative 0.1. Get the difference, then the answer will be 1.0112. It's positive. It means it is stable. Okay. When it gets negative, it is unstable. It means it has tilted so much. Okay. That's it. I hope you have understood it. And now your homework, of course, for stability, this will be homework number 4. Homework 4 is the same as what I have in this video. Please illustrate and do the calculation similar to what I had in this video. All right then, bye for now. And I will send this copy to you and the link of the video. Okay, bye. And just review it. If you have the copy, then maybe you can just go through it without the video. But if you want if you want explanation, then you can review the video. Okay, bye, and see you around. Tomorrow is Thursday. I guess I'm not meeting the fluids as well, because anyway you have everything. You just have to do the homework and review, because a Monday is the start of the exam already. Right on Monday morning will be the start of the midterm exam. Okay, I don't like to disturb. I don't like to give anything, but you can come and visit us in our room. I will be there. You know where my room is. You know our room, MCDP 301. I will just be there. Okay, tomorrow, inshallah, everything will go well, and there will be no disturbances as to the weather condition. Bye for now. Keep safe and hope to see everyone alive and kicking. Right, bye. Just prepare for the exam. I will see you. Okay. Thank you. Bye for listening, and bye for now.